Welcome everyone. I am very happy to present a recent project to you which consisted of building an automatic speech recognition system for Bashkir. My name is Monja Burkhardt and my colleague Aigiz Kunafin, who is the one who actually started the whole project and implemented the model, is available on Slack and will be able to already answer any questions while I am presenting. So let me briefly explain why I find this topic so interesting. Before going into data science and before joining TrustBit, I was working as a linguist at the university. So this is me some years ago. And what I'm doing here, maybe you can see these waveforms on my screen. I am transcribing speech data. It was for a huge project for which we collected a huge amount of Spanish audio recordings, and I spent a lot of time transcribing them. We soon realized that it takes about, for only just 5 minutes of speech recordings, it takes about 1 hour to transcribe it. And at that time we had about 120 hours of speech recordings, which corresponds to more than 1,400 hours transcription time. And if you were to translate that into money according to the usual hourly wages, I guess you get an idea of how valuable and really expensive this transcribed speech data is. And as we will see later, this is also the kind of data which is really central for building an automatic speech recognition system. A brief overview of what I will talk about, and I have to say right away that this presentation is more of an commented reference list than an in-depth explanation of the model. Therefore, I have provided you with an extensive list of papers and blog articles in the appendix. So if you are really interested in the topic, I recommend you to go through it and to read it. But I hope I can still give you a rough overview about the purpose of implementing the model, then the model per se, and fine-tuning, and of course about its performance. Spoiler alert, it worked very well. So what is the motivation behind it? Aigiz is a native speaker of Bashkir. This language is mainly spoken in Bashkortostan, and it has about 1.4 million speakers. But for many of these speakers, Bashkir is not their main language, and it's not very present in the digital world. And this is especially a problem because children, as we all know, are interacting more and more with the internet. And if everything is just in Russian or English, maybe they only learn these languages and there's no need for them anymore to really use Bashkir language. And therefore the mission of Aigiz and of course of some others is to, in some way digitalize the language to preserve it. And for this purpose, Aigiz organized and managed a volunteer campaign to record speech data using Mozilla Common Voice, which is a platform for collecting speech donations to create public domain data sets. And at the moment there are more than 250 hours of labeled speech data. When I say labeled speech data, I mean audio aligned with the text. And one of the first steps to digitalize the language is to implement a speech-to-text system, and the key technology here is automatic speech recognition. So the goal of speech recognition is to convert audio waveforms, which can look like this, to readable text, or at least readable for anyone who understands Bashkir. So what's the model Aigiz used for that? In this overview, you can see that in recent years, many models for automatic speech recognition have been developed, which have also become larger in terms of the number of parameters they involve. Aigiz used one of the most recent ones, which is called XLSR, which was released by Facebook, Meta AI, and Hugging Face. Yeah, but I will actually not say much about it because it's to a high extent the same as an earlier model, which is called Wave2Vec 2.0. So yeah, it is important to first understand what Wave2Vec does. And the main idea of this Wave2Vec is quite simple. It consists of two phases. Phase one is a self-supervised learning setting. I will come to the concept of self-supervised learning in a minute. And yeah, for this phase, a large amount of unlabeled data is used to pre-train the model. And this is still a very general model which can be used for different downstream tasks, such as machine translation or, as in our case, automatic speech recognition. And it really depends on the task, which kinds of model are used in phase two. So in phase two, the model is fine-tuned with the help of labeled speech data. And here comes the main advantage of this Wave2Vec. You don't need tons of labeled data, and as we have seen in the introduction, this is really the data that is really hard to get and expensive. So especially for smaller languages, for languages where you don't have so many resources, this is a huge advantage. And one reason why unlabeled data is sufficient for pre-training is that Wave2Vec 2.0 relies on self-supervised learning. What does that mean? It means that it doesn't require manually added labels, but it somehow generates the label by itself. And it's very easy to understand that if we take text as an example. Imagine you have a text and then you hide or mask single words, and then you let the model learn which words are missing using the surrounding words. And then, you can say that in theory, the data is not unlabeled anymore because the algorithm knows which words were taken away and can take them as labels. So this is for text. With audio, it works in a very similar way, but we will come to that later. First, I want to dive into the model architecture. Okay. So let's begin from the bottom. So here we have the audio signal, and the very first important component is the feature encoder. And the feature encoder's job is to reduce the dimensionality of the data. It encodes snippets of about 20 milliseconds of audio. So these are very, very short waveforms. And they are transformed to vectors in a way that waveforms that are similar in terms of prosody, for example, which is a speech melody, so to speak. These similar waveforms will be represented by vectors that are close to each other in the vector space, in so-called latent space. And after that, there are two things that are going on. On the one hand, these vectors, Z0 to ZT, are fed into the transformer layer, and this is the so-called context network. And this is where multiple time steps are combined, so the output are contextualized representations which cover a larger span of up to 1 second. But before this contextualization happens, some of the speech representations are masked because, as I said before, it relies on self-supervised learning. And just as before, where single words were masked and the surrounding words were used to retrieve the missing information, here some of the speech representations that are masked. You can see here these grayish ones are the masked ones. So, for example, if this Z1 is masked, since this C1 contains information from the surrounding vectors that are not masked, the information in C1 can be recovered from the context. So these are two very important components. But the question is, how does the model learn? And here the concept of contrastive learning comes into play. Contrastive learning is a concept in which the input is transformed in two different ways, and afterwards the model is trained to recognize whether the two transformations of the input are still the same object. And yes, there's of course a loss function that compares the two outputs. In our case, the first transformation is here the transformer layer, and the second one is the quantization module. So what is quantization? One of the major challenges of processing speech is its continuous nature. So unlike written speech, where you can have the single words and you can take them as discrete units, natural speech doesn't have these natural subunits. I say natural subunits because in linguistic theory we of course assume that there are some units, we call them phones, which are the actual sounds, for example p, t, z, and the number of phones which can occur in language is finite but really large. So it would be very inefficient to have to tell a model for each language which possible phones can occur. So what we want is that the model learns it by itself. So yeah, in a nutshell, what this quantization module does is to convert values from a continuous space into a finite set of values in a discrete space. So it's roughly nothing more than a mapping function. And its outputs are the so-called quantized representations. And importantly, these quantization, this is done before the masking takes place. And these quantized representations, Q1 to Q2, are targets of our contrastive learning task. So the goal is to identify the correct quantized speech units for the masked positions. So yeah, this is the rough idea how pre-training works in wave-to-wake. And the question is, how is XLSR, the model Aigiz, used different to this wave-to-wake? And the answer is, well, yeah, it's not so different. The main idea of the XLSR is, or like the ideal goal of this XLSR is to have one model for ideally all human speech. So it's trained on many languages to obtain more general cross-lingual speech representations. And yeah, this was the pre-training. And what we now need to do is to align that with the transcription. So this is the actual task we want to solve. It could also be classification or machine translation, but in our case it's speech recognition, and this is where we really need the labeled data. And yeah, as I mentioned before, luckily we have labeled data. Yeah, we have over 250 hours of labeled data for Bashkir. And the mapping of the context representations to the corresponding transcription is done by adding another linear layer on the top of the wave-to-wake model. And this is called connectionist temporal classifier. And here I'd just like to refer to the linked blog post, which explains it very well. In short, what it does is it takes all possible alignments of input sequences that could map to the output sequence. Here it is, the cat, and it adds them up. And and this is then the probability of the output sequence. And in theory, we are done here because the CTC aligns each contextual representation with a transcription, which is perfectly fine. And many speech recognition systems stop here, because it can already lead to pretty good results. But there can also be some problems because so far the recognition system is almost only based on the acoustic input, and which is then mapped to the most probable transcription. But now consider words with the same pronunciation but different spelling, so-called homophones. For example, in English there, the pronoun and the adverb there. And yeah, until now, the model can't really decide which of the two makes more sense in this context. And such confusions or misspellings can happen. So what we can do to reduce this risk and to yield a more accurate recognition is to include a language model. And yeah, one solution is to predict from a sequence of words the next word that is most likely to appear. And a common choice to do that are n-gram models. And n-gram models are exactly that. They predict the occurrence of a word based on the n-1 previous words. In our case, Aigiz used 5 grams. That means based on the 4 previous words, the next word is predicted. And for that, one just needs text data. Yeah, and text data is not that easy to get, not that difficult to get. And there's a library with which one can train such n-gram models. And I also added some references about it in the appendix. And as I already said, performance can really be improved here. And speaking of performance, I guess you are all already very curious about the results. The metrics that are commonly used here is word error rate. And yeah, the formula is like this. Imagine a sentence which is the output of our model. And then you compare it to the actual sentence in the test data. And the word error rates would count all deviations from the actual sentence, which can be insertions, deletions, or substitutions. And then you divide it by the number of words in the actual sentence. And here are some example values, which are the result of some previous works. You can see for comparably large data sets, like for example this German data set include also over 250 hours of speech data, and they reach values about 10. And finally, Aigiz result is 0.04. He participated in a Hugging Face competition, which was about building an XLSR model, and with this model, Aigiz placed third. And one reason for that good result could be that, according to Aigiz, Bashkir is a language with a high degree of grapheme-phoneme correspondence, which means that if two words are spelled differently, it's very likely that they also pronounced differently, so there are very few of these homophones. And another reason could be that the language model is very good that he included. And yes, of course, from here you could build other tools like machine translation, and here you could really use the same pre-trained model and just use another fine-tuning technique. And in any case, this result is not only great because Aigiz won a prize for that, but of course it's a crucial step towards the preservation of the Bashkir language. And with this, I want to say thank you.